Scheduling with Contingent Resources and Tasks, delivered by Jussi Rintanen.
Yes, thanks. This is the only microphone, right? Yeah, okay, so I have to stand here. Yes. Yeah, so the topic of the talk is complexity of contingent scheduling. So this is about finding out what are the actual resource requirements for solving contingent scheduling problems. And the results are expressed in terms of complexity classes, mainly in the polynomial hierarchy and p-space. And well, there have been several different approaches to handling uncertainty in scheduling. Basic approach, similar to replanning in planning, is the reactive approach. So we schedule the task somehow, assuming that there is no actual task failures or anything else unpleasant happening, and start executing your schedule. And well, if something fails, you schedule again. This approach is, of course, it's incomplete or incorrect depending on how you define it, and there are actually formally much better approaches, including the redundancy-based approach. You allocate more resources that you might actually need. It's just in case to handle situations where you run out of time because of some delay. And the probabilistic approach, you find the best unconditional schedule that observes the possibility of failures or delays, but well, doesn't actually work differently in different kinds of situations. And then the most general approach is the continuous scheduling approach, where you actually anticipate different kinds of things that might go wrong during the execution of a schedule, like something takes longer than anticipated, some resource is not available, some deadline of some task will be earlier or later than anticipated, and so on and so forth. So the last approach is the one addressed in this talk. In terms of complexity results, there are two main ways of evaluating the quality of a schedule. So much work on several areas in planning and scheduling is looking at the expected cost of a schedule. So you look at all the possible execution of a schedule, and then you look at the expected value. So some kind of average of the individual executions of a schedule, and you calculate the expected value or cost of a schedule. So this is one possibility. This is very good possibility if you are scheduling lots and lots of similar problems, and you're not actually interested in the individual success or failure of a schedule. So it doesn't really matter in this particular case your schedule is going to be bad if overall on average you are doing very well. And another possibility, which is the topic of this talk, this affects the complexity classes I will be discussing later, is the worst case cost of a schedule. So of all the execution of a schedule, we are looking at the worst possible scenario that might happen. So how bad might it be? Given this schedule, how bad might the result be, considering all the possible failures and delays and so on and so forth. This is more interesting when, for example, you have only one problem at hand, not a long sequence of problems, and it's very critical that you get your schedule executing your specific case very well. So you might not care that the failure is unlikely, but if you want to really guarantee that things go well, you have to look at the worst case costs. And of course, this is essentially a form of risk averseness. So you want to avoid the bad situation. You're really scared of the bad situation or bad outcome. So then you have to be looking at worst case costs. The complexity results are not, in some cases, known a little bit, but mostly this area is quite uncharted. So basic cases are, for example, in the expected cost scenario, is that if you have a possibility of delays of tasks, something might take a little bit longer than anticipated, then the problem of checking whether the expected cost of schedule is below certain bound or not is sub-P hard. It's probably also sub-P complete. And I think in general case, for the expected cost, the problem is P-space complete. If you also consider other kinds of failures like resource not available, earlier or later deadlines, or something else. In this work, in this talk, I will be focusing on worst case costs. These have not been really addressed in earlier research. I will show in two different formalizations, slightly different kind of uncertainty or failures, that the problem is P-space complete. So question whether there is a schedule that in the worst case has a cost of something, that decision problem is P-space complete. And then I consider two special cases, full observations, meaning that you actually know, well, after you have found your schedule, but before you start executing, you know what will be the resource availability during the whole execution of the schedule. In this case, the complexity will be pi p2 complete, a low level in the polynomial hierarchy. And the third, well, a second specific result is that when you construct contingent schedule that has a small size, small means polynomial size, the problem will be sigma pi 2 complete. So this is also low level in the polynomial hierarchy. I will, in the last slide, say something about the implications of these last results on the kind of algorithmic techniques you might be using when solving contingent scheduling problems. Worst case cost measures are quite a bit different from the expected cost measures, and the thing here is that because we are looking at the worst case, if something can go wrong, in the worst case it will go wrong. So if everything can go wrong, in the worst case everything will go wrong. So in most cases you will not be able to do any kind of interesting scheduling at all because the worst case might always show up and okay, in the worst case you can't do anything at all. So we have to have some assumptions, so limit the kind of failures and uncertainty that is that might show up during the execution. And I view two specific kinds of things, so or three specific kind of things. So, for example, some resource might not be surprisingly available during the execution, but if this resource is not available, there's always a guarantee that some other resource will be available. So if something is not there, we know that something will be there to, well, substitute for the first resource. And another possibility is that we might not actually have to complete all of the tasks in the schedule. So if we cannot actually complete some task, there will always be some substituting task that is also sufficient and good. So if this is not possible, we will complete some other task. This is sort of a similar flavor as the alternative resources case. And the third possibility, if some resource is not available, okay, any task that necessarily depends on that we will not be able to complete it, but we allow also the case where a specific task can be completed in multiple alternative ways by using different resources. So these are the things we guarantee that also in the worst case we are not completely out of luck, and we still can often find schedules satisfying certain cost bounds. Our formalization of scheduling is pretty general, so this is supposed to include all kinds of standard job shop scheduling, open shop scheduling, and this kind of thing. So we have task resources. Each task can be completed with certain resources in a certain time. We have a partial order relation on the tasks, telling what are the possible orders these tasks are completed, and there's a symmetric non-simultaneity relation on the task. So certain tasks, for example, belonging to the same job cannot be taken simultaneously. And then there's, from the last slide, these alternative resources, alternative tasks, things. We have Boolean formulas that say which tasks are sufficient to have the overall scheduling problem solved. So this can contain disjunctions. For example, saying complete T1 or T2 or T3. Any one of these tasks is okay. If you complete one of these, you're fine. And similarly, we have a Boolean formula, again, containing disjunction and conjunction and negation and so on, indicating what kind of resource combinations are possible, what kind of, what is guaranteed to be available during the execution time. And then the important thing here for the contingent scheduling to be interesting at all is that we have uncontrollable resources. So Some resources, they are always available. We can just choose which resource we will be using. But some resources are uncontrollable. They might or might not be available. However, still satisfying these Boolean formula delta that tells us what is guaranteed to be available during the execution in any case. And lastly, there's observation horizon telling how far to the future can we see. The most difficult case is that during execution of schedule you only know what resources will be available right now, but you won't know what is going to happen in the future. And of course, if the horizon length is short, scheduling will be more difficult. In the extreme case, the horizon is infinite. When you start executing schedule, you can see everything, what will be and what will not be, what resources will and will not be available in the future. And here is some properties of scheduling problems I will be using in the next slides. So uncontrollable resources, this property, when the set of uncontrollable resources is non-empty, so some of the resources can't be controlled. Alternate tasks, we have actual disjunction in the formula describing what tasks are sufficient. Alternate assignments for a given task, there might be several resources that can be used for completing it. And alternative resources, we have actual disjunction in the formula describing what resources will be available. In this case and this case, the basic case without uncertainty simply means that we have a conjunction of all tasks and all resources telling that all tasks must be completed and all resources are available. When we have uncontrollable resources, we always assume that the alternative resources property holds. Otherwise, those resources, in the worst case, would not be available and therefore completely irrelevant. So this is just to make the problem meaningful in these cases. Here are the main results for the p-space or for the most general case. So if we don't have uncontrollability, we have the basic usual scheduling case which is NP complete. So practically all interesting scheduling problems are NP complete. They are contained in NP because there is no uncontrollability. There is full information, you can schedule any way you like. Doesn't make a difference whether you have alternate tasks or alternate assignments. And then there are these two more interesting problems, uncontrollability, and we have showing both two cases, alternate tasks and alternate assignment case, that either one of these will make the problem p-space complete. And and having neither of these, the problem again becomes trivial. We don't consider that case. The first p-space, okay, so the first of the p-space completeness results relies on a proof technique that I demonstrated here briefly for the standard completely controllable full information scheduling case. This is of course a known result, so it's very well known that basic scheduling problems are NP hard. This is used for the proof of the next result. So the idea here is that we have alternative tasks that corresponds to clauses in the three-sat problem. So one of these tasks have to be completed. Each task can be completed by exactly one resource. And intuitively these mean a literal and a positive literal and negative literal. So these are exactly the literals in the three-sat problems. And then we have at each time point we have one of these two literals available. So either something is true or something is false. We can choose which one. So we can make every proportional variable true or false. And we can use each resource for completing three tasks. And I should say here that we are looking at the three-sat problem restricted to maximum three occurrences of any proportional variable. So this way this reduction here actually works very well. So at each time point we choose either use these resources or these resources and can complete certain tasks. Step by step going to this whole thing, and if the scheduling problem has a solution, okay, then the three-sat problem is satisfiable and the other way around. So simple reduction from sat to scheduling. shows that problem is NP hard. And the interesting thing here is that, okay, we choose truth value assignment, the schedule chooses truth value assignment and shows the certain proportional formula is true or false, or it is satisfiable. And now for the contingent scheduling case, when something is uncontrollable, we can modify this reduction very easily to handle QBF, unlimited, otherwise unlimited quantified Boolean formulas, except that, okay, we still consider the body of the QBF phi to be consisting of 3 literal clauses with at most 3 occurrences of any proportional variable. So, now the trick here, in comparison to the previous slide, where we could show for each of these blocks whether you use the positive or the negative literals, here some of these blocks are uncontrollable, corresponding to the universal quantifiers, universal variables. There the environment chooses whether literal is true or false. And this will then exactly correspond to the evaluation of quantified Boolean formulas. And quantified Boolean formulas truth is a piece-based complete problem. And the result will be that schedule exists if and only if the quantified Boolean formula is true. Schedule exists and only for all possible environment choices, there are schedule choices that lead to successful completing all required tasks. And this exactly corresponds to QBF evaluation. So this is the piece-based hardness part. Piece-based membership is easier to show. I don't result the result here. And yeah, this was for alternative tasks. We can also easily show that for alternative assignments, the piece-based hardness holds. So here the idea is that we will have a similar choice of valuation here. We have a similar choice of valuation here. Each task has to be completed with the, each task has to be completed, but we can use 2 alternative resources. There's a short resource corresponding to the valuation we are picking up in the earlier proof, and a long resource with the longer duration. And the idea here is that if there is a valuation, if the QBF evaluates true, we can fulfill each task or complete each task by using the short resource. And the total duration of the schedule will be 3n plus 4n plus 4n. But if some of the clauses cannot be made true, completing the tasks related to that clause have necessarily a slightly longer make span, and that's how we can exactly, again in this case, do a reduction from QBF to contingent scheduling. Then there's two results placing contingent scheduling problems in low levels of the polynomial hierarchy. If the observation horizon is infinite, or in these previous results we have the most difficult case of only one step ahead observability. So if observability is infinite, we have a p-pi2 complete problem. So when starting the execution of schedule, we have to have the contingent schedule ready, but we can observe everything and then choose the right regular schedule to fulfill all the tasks or complete all the tasks. That's one of the easy cases. Another easy case is when the contingent schedule has a small polynomial size, and in this case it will be basically the complexity on the second level of the polynomial hierarchy, because we can simply guess, we can construct a polynomial size or guess a polynomial size schedule, and then we can, using an NP oracle, we can verify that this polynomial size contingent schedule actually works correctly in all cases. These are considerably simpler results. The interesting thing is, all of these results is that the complexities are exactly the same as in contingent or conditional planning, given the restriction to polynomial execution length. So if execution length is polynomial, otherwise we don't limit the size of the plans or observability. So observability can be anything, including very little observability. We get a piece-based complete problem. And with the same restriction we had here, full observability with arbitrarily big plans, or small plans and arbitrary partial observability. We get similar PI2 and Sigma Pi 2 complete planning problems. So actually in all of these cases the complexity in scheduler and contingent planning is exactly the same. The main implications in this is of course that anything outside NP makes the use of standard constraint programming SAT CSP methods very difficult for planning. So if you have a very limited amount of uncertainty, it is easy to do the reduction to standard methods. You slightly explode the size of your whatever constraint program, SAT problem or CSP problem. But when you have unlimited uncertainty about the resource availability, these reductions will always have an exponential size. So this does not typically provide a practical solution method. So theoretically, these are the things we should be using, but the disadvantage of these things is that solver technology in this case is not at anywhere near the level we can solve problems inside ANP. Yeah, thanks.